Okay. I have 22 grams of sodium metal, which is brought into contact with 22 grams of carbon dioxide gas. The mixture is heated, and the following reaction occurs. This is a really neat reaction. We've done it over here in the lab. You get a solid flame when you heat the mixture. It just glows orange. We've got it in small samples. We get it. Once it starts, you take away the heat, and it continues to go. It sustains itself. It glows this beautiful orange color. And I've seen them last about 30 seconds before it's all over. And you're left with this black charcoal looking material, which I'm just calling carbon. And it turns out it's a little more neat than that. I like this is just for a little more background. Okay. This is pursuing the line of thought that the carbon dioxide, which is the bad boy of climate change and politically right now, it's not a waste material. It's a very useful feedstock. I mean, plants have been using it for billions of years to their advantage. And I hate to be outsmarted by a plant. And so this is just one of the many useful reactions that use carbon dioxide. Okay? And so this is a good question. I'm using it for the limiting reagent, theoretical yield, an actual yield question, but it's good for anything else as well. So what do I want to do? How do I approach this problem? How would I start? I'll give you a clue. Always look at the whole problem, because first I'm asking what's the limiting reagent. Next I'm asking what is the theoretical yield of sodium oxide. So that's your tell. You want to go, I'm going to want to cast this, given the known starting amounts, using the mole ratios, I'm going to want to find out how many moles of sodium oxide is produced from either of the starting materials, and you're going to have to demonstrate it with both to answer the actual question. So you read ahead, and you're going to want to carry it to the point where I know how many moles of sodium oxide are produced from each, assuming that it goes completely. Okay? And so, in that regard, what will I start with on the left-hand side? I'm going to do it first, since I'm going to ask for sodium. What do I start with on the left-hand side? So I'll go 22.0 grams of sodium, and label it, please. Include the full labels. What do I go from grams to? Moles. Moles. And there's 1 mole of sodium. And notice it's just 1 mole. Always is going to be that way. We'll get to the mole ratio in a little while. But for now, it's always 1 mole of sodium for every, turns out, I'm using, I gave you that it's 22 grams of sodium. Okay, now where do I want to go? Moles of sodium to what? Moles of sodium oxide. And what do I use, that's what the balanced equation was used for. So what do I use there? The mole ratio, what is it? I have 2 moles of sodium oxide for every, and don't, please resist the temptation to skip a detail. Don't round this off. Leave it in the raw form. Use the information, these numbers, don't round them off, because 2 divided by 4 turns out to be easily simplified, but don't do that yet. Okay? For every 4 moles of sodium. And that's going to be equal to, so I got 22 divided by 22 is 1, right? Okay, and so 1, and now 2 divided by 4 is what? 1/2, or 0.5, equals 0.5 moles of sodium oxide. Now, I'm going to do the same thing with CO2. So I start on the left-hand side with, how many grams do I have? 22 CO2, and there's 1 mole of CO2 is 44 grams of CO2. And what's the mole ratio here? 2 to 1. There's 2 moles of sodium oxide for every 1 mole, and I sort of, okay, you'll have enough room on the test, but you're going to have to make sure that you write it in the appropriate margin for every 1 mole of CO2. And that's equal to, okay, 22 divided by 44 is what? 1/2. And 1/2 times 2 is, so I got 1.0 mole of sodium oxide. Okay, now is there enough information to answer the question? Which is the limiting reagent? Okay. So, therefore, sodium is the limiting reagent. In other words, I cannot, if this reaction goes completely as written, it cannot give me, I'm limited by the sodium. I can't get any more than this. So that's my limiting reagent, and we've all done all the heavy lifting, and that wasn't even that heavy a lifting, to answer the next part of the question. What is the theoretical yield? Well, I already know there's 1/2 mole. The theoretical yield is the yield you would get. What's the definition of theoretical yield? Yield I would get under what? If what? If it what? I didn't understand what you were saying. I'm sorry. It's
something like actual over measure.
Well, no, the theoretical yield. What is the theoretical yield by definition? It's the yield you would get under what condition? Ideal conditions. That means assuming this goes 100% as written. Okay, which is an ideal assumption. Seldom occurring in the real world, but it does in fact happen on unlimited occasions. And most of the time that's not the way it works out, but the theoretical yield. So I know I'm going to start over here on the left-hand side with what? Zero point 0.5 moles of sodium oxide, and I want to multiply it times what? Grams per mole. So it turns out to be 60 grams of sodium oxide for every 1 mole of sodium oxide. And that turns to be a trivial calculation, as well. Multiplying times 0.5 is the same as dividing by what? 2. So what is the answer?
30 grams.
So I end up with 30 grams Okay, now we've answered the second part of the question, part B. Now we get to the third part of the question. I actually, in the real world, I obtained 15 grams of sodium oxide. What is the percent yield? Now we go to the definition of percent yield that you were mentioning earlier. What was that again? What is percent yield? Okay, for those who couldn't hear what he said, the percent yield by definition is the actual yield divided by the theoretical yield. Okay, and so this turns out to be, again, a very simple, and multiplied times 100%. So I'm going to get the percent yield. Is equal to 15.0 grams divided by 30 grams. And that one turned out to be a pretty trivial calculation as well. The numbers weren't a problem. What is it? 50%. Okay? Are there any questions about this one? Yes?
Just a clarification. When you say limiting reagent, are you referring to limiting reactant?
Same. We're just it's a question of semantics at this point. I could, yeah, it's the limiting reactant, limiting. I like to use the example we'll be talking about tomorrow in the lecture. Let's say I'm going to open up my little sandwich factory. Decide to go into business, and I'm pretty not very creative. I'm going to have 2 slices of bread and 1 slice of cheese. This is not probably going to be a good sandwich factory. It's just a sandwich factory. I have 2 slices of bread and 1 slice of cheese go into each sandwich. And if I go out to the Smart and Final, and I get 42 slices of bread and 11 slices of cheese.
So it's the same thing, you're just calling it something else.
How many sandwiches can I make? My theoretical yield, or my limiting, well, we're going to get to how many sandwiches can I make? What's my theoretical yield going to be? Ideally. What am I going to be limited by? I have 42 slices of bread and 11 slices of cheese. Yeah, I'm limited by how many sandwiches can I make? What? No. If I have 1 slice of cheese for each piece of bread, for each sandwich, I can make 11 sandwiches. So obviously, the limiting reagent's the cheese. See what I mean?
Okay, I just wanted to know if it's the same thing as reactant.
Yeah.
Just the words.
Yeah, the words. Yeah, I understand. I maybe over-answered your question. But I like to use that example because it's a better, it's easier for visualization. We use bicycles and tires and all that other stuff. And, sandwiches, just to illustrate what limiting reagent is, the limiting reactant, same. And, just as long as you're clear on the definition, it should be clear. And theoretical yield. Now, I want to continue that example just so I can wrap it up. Okay, and I go into production and I actually eat one of the sandwiches. And then I drop, I drop several on the ground, and I end up with 5 sandwiches. Or let's say 7 sandwiches. So my actual percent yield would be 7 divided by 11 multiplied times 100%. So, because in the real world, that's what happens. We don't always get 100%. The theoretical is the ideal. Okay. So that was a pretty cheesy example, I agree. Is there any other questions? Then that's over. Okay.